Hi, everybody. So I wanted to complement our examples of normal subgroups with a few more non-examples of things which are not normal subgroups. So let's start with looking at the dihedral group again. But this time, instead of taking the subgroup generated by the rotations, I want to take the subgroup generated by a reflection. So as usual, I'm thinking about the dihedral group when n is at least 3. And so we have a rotation and a reflection. And I'm going to let H be the subgroup of order 2 generated by E and S. And since H has 2 elements and Dn has 2n elements, we know that the number of cosets, the index of H, which is the number of cosets, is n. And we can find those n cosets by taking elements of Dn which are not in H and looking at the coset that they yield. And we need to come up with n of them. And the way to do that is to use the rotation. So if we look on the left, first of all, we have H itself. And then we can take the rotation RH, R squared H, all the way down to R to the n minus 1H. So there's n of these. And they give the left cosets RRS, R squared S, and so on, down to R to the n minus 1, R to the n minus 1S. But if we do the right cosets, so we would have H, HR, down to HR to the n minus 1, these would be ES, ESR, sorry, RSR, all the way down to R to the n minus 1, SR to the n minus 1. And again, we have n cosets, and they're different from one another, n different left cosets, n different right cosets. But if you look at the right cosets, you see that when you have RSR, that's the same as R inverse S, where we use the basic rule in the dihedral group that SRS is R inverse. So we move S past R, but it becomes R inverse. And similarly, all the way down to the end here, now we have R to the n minus 1, and R to the 1 minus ns. And from this, we see that the left cosets and right cosets are actually different, because the right coset HR and the left coset RH are not the same. One has R and RS, and the other has R and R inverse S. And those elements are different. R and R inverse are different. And so the left cosets and the right cosets are not the same, and therefore H is not normal, because its left and right cosets are not the same. For another example, let's take Sn, the subgroup Sn, and let's take the subgroup generated by a 3-cycle in Sn where n is at least 4. So our 3-cycle has the form ABC, and the subgroup H consists of the identity, the 3-cycle ABC. Here, A and B and C are all different. And then if you do this twice, you get ACB. That's our subgroup of order 3. And now, why did I care that n was at least 4? Well, I want to show this is not a normal subgroup, and I want to choose D different from ABC. And I can do that if I'm dealing with permutations of at least 4 elements, because I've only got 3 elements mentioned here, and I take the other one. So if A, B, and C were 1, 2, and 3, I take 4. And I look at, let's say, the transposition R to be just the transposition AD. And let's look at the left coset, ADH. Well, that's AD, and then AD times ABC, and then AD times ACB. And that is AD, and then here we have A goes to B, B goes to C, C goes to A goes to D, and finally D goes to A. And then we have A goes to C, C goes to B goes to A goes to D, and D goes to A. So that's the left coset. The right coset is again AD, but now we have ABCAD and ACBAD. And that's AD. Then we have A goes to D, D goes to A goes to B, B goes to C, and C goes to A. And then in this one we have A goes to D, D goes to A goes to C, C goes to B, and B goes to A. And if we compare these two, we see that they are not the same. Because, first of all, the only possible right coset which could be the same as this left coset is this one, because they have an element in common. And so this one here is the only right coset that contains AD, because if AD is in this coset, it can't be in any other coset. But then we see these aren't equal, because here we have A goes to D, whereas here we have A goes to B, and here we have A goes to C. And in both of these, A goes to D. So the permutations which occur other than the AD are different. And so this subgroup is not normal, because we found a left coset and a right coset which are different. The last example of a non-normal subgroup that I wanted to give is a matrix example. So I want to consider the subgroup H consisting of upper triangular matrices 1, x, 0, 1. Here x is a real number. Because these matrices have determinant 1, they're invertible, and so this is a subgroup of GL2R. In fact, if your matrix, let's say H, is 1, x, 0, 1, then H inverse is 1 minus x, 0, 1. And in fact, H is actually isomorphic to the additive group of the real numbers. So it's an abelian subgroup of this infinite non-abelian group. And I claim it's not normal. And here we're going to use the GHG inverse criterion. We're going to take G to be the group, the matrix element 0, 1, 1, 0. And we're going to compute GHG inverse, using the fact that G inverse is also 0, 1, 1, 0. Because you can just do a matrix calculation that G inverse is 1, 0, 0, 1. And what is GHG inverse? Well, it's 0, 1, 1, 0 times 1x, 0, 1 times 0, 1, 1, 0. And that's equal, because G is equal to G inverse. So let's do this matrix multiplication starting on the right. We have x, 1, 1, 0, which then works out to be 1, 0, x, 1. So the effect of GHG inverse is to flip the x from the upper right-hand corner to the lower left-hand corner. And so the subgroup GHG inverse is the collection of matrices 1, x, 0, 1. And these are certainly different. So, so this subgroup H is not normal. So that gives just a couple of other examples of non-normal subgroups.